Thank you very much, Werner, and thank you very much for inviting me. It's really great to be here. I'm not sure whether I can follow the previous talk, which was really hugely immersive for me, which was funny. So I'm going to talk a little bit about the future, but I'm also, again, have to establish where we actually are. First of all, geographically, I'm based there. This little red arrow, which you might see up there, is St. Thomas's Hospital. It's one of the UK's major teaching hospitals. We are directly embedded within that. This is the place I don't really want to speak about these days, just opposite the House of Parliament. But we also have a Ferris wheel. And actually, my office window, I can see that. And I can't see the Parliament. I'm very proud of that. So there you go. So this is where we are on a London map, directly at the Thames. Our school is a School of Biomedical Engineering and Imaging Sciences. It has about 600 I would say superheroes from all different disciplines, because that's what imaging and biomedical engineering takes. We have there physicists, engineers, computer scientists, but we also have academic clinicians or clinical academics. So we've got 6 departments, and 3 of them are actually in cancer imaging, cardiovascular imaging, and perinatal, so fetal neonatal imaging. But then we've got also traditional engineers, and now we're going into surgical interventions and guidance, and virtual reality, I'm sure, will have a key role. So that's us. So I want to talk a little bit about computer vision and biomedical imaging. So bio is always a bit in brackets. Mostly it's medical imaging, but a lot of things we do, we start in preclinical imaging, which is the posh name for animal imaging, and we always have to be careful when we use those words. But computer vision, as probably all of you are aware, is the science where science and technology of machines that see. So that was always the vision of computer vision, and we're getting there, I think, with self-driving cars, for example. And so we want to really look there into the theory and technology for building artificial systems, which allow us to extract information from images or even non-imaging data these days. Most efforts, I would say, and I hope I'm not unfair to my colleagues there, is on 2D images, photographs, real images, or real pictures, as we call them. Some on stereo vision to reconstruct 3D scenes from different viewpoints, and video sequences. So it's very much based on photography as the main sensor. Yeah? Whereas in medical imaging, we are looking inside of our body. Yeah, we actually really want to visualize what's inside of us. And that's done for clinical diagnosis, for planning interventions, even during interventions. And we really want to see our organs. We want to see how they interact. We want to study their function in neuroscience, looking at kids' brains versus adult brains, for example. And the efforts there in the actual imaging modalities are basically everything you can think of in what's done in any radiology hospital like the one here in Vienna. So it starts with X-ray there, Röntgen rays, as we call them in German, ultrasound, magnetic resonance imaging, computer tomography. So these are more like anatomical imaging technique where you see the structure of the body, but you can inject contrast, so you actually can understand a little bit the function, the flow of the blood, for example. But then there's also nuclear medicine imaging, like positron emission tomography, PET, and SPECT imaging, which really only give you the function. And our challenge quite often is to merge these different sources of information so we actually can understand what's going on. There's also more 2D imaging, microscopy, fluorescence imaging, and histology imaging. And there's, I think, a more direct link to computer vision because the image analysis tasks are quite similar, and the dimensionality of the data is quite similar. So computer vision, I think, started with the invention of photography in 1826 by Nicephore. I maintain, because I'm at King's now, actually it starts when things got into color with James Clerk Maxwell in his most productive years at King's College London before he buggered off to Cambridge, was to do his first color photography. In fact, it wasn't him, it was his lecturer, Thomas Sutton, who actually did it, but Maxwell got the claim. And if you remember Maxwell's equations, magnetic fields, field strength, area, surfaces, electricity, binding all these things together, magnetic resonance tomography is actually based on those physical principles which were established, those relationships between those equations that Maxwell came along. So it's quite a nice link there between computer vision and medical imaging. So images in computer vision these days are, of course, real images. You can look at ImageNet, which came, I think, 2010, which created this huge increase of people working in computer vision at the time, because all of a sudden they had enough data. And you can sort this database for images with traffic, with cars and traffic lights, or into musical instruments, flutes and guitars, or animals, anything from little cats to sea lions, and indoor and outdoor scenes. So people all of a sudden had a lot of data to play with, and it really is a lot of data. Yeah, it's millions, if not now billions, of images. Parallel to that, Google Images also came along, but it wasn't sorted, it wasn't annotated. But everybody of you contributes to Google Images if they're uploading your pictures to share with your friends. So this is all, thanks to you as well. It's a huge crowdsourcing effect there. Now, medical imaging started, I would say, with Leonardo da Vinci. There's another interesting link, perhaps, with computer vision and medical imaging, because what predates all of that is the invention of the camera obscura, which was, I think, 400 before Christ, somewhere in China. Yeah, so the pinhole camera, which made this possible. But Leonardo was the one who actually started drawing very meticulously the cardiac muscle, the veins, the arteries, the skeleton, so people could actually see how things were like. He must have been somewhere in a basement of a very grotty hospital in medieval Italy and studying cadavers to do that. Yeah, so he had to open them up and or have somebody else open them up and actually draw them, because he couldn't look inside, of course. Vesalius is another person, and then for maybe some Dutch members of the audience, Rembrandt, of course, Grand Master. This is like an intervention. He was painting a famous surgeon, Nicholas Tulp's lecture on anatomy, where he actually very nicely depicts what happens if you open the hand and the wrist and all the ligaments and so on. So, but people always wanted to look into this. For me, the real start was actually Röntgen. The most amazing thing about Röntgen is he accidentally stumbled across this new thing. Really, it was a complete freak accident in his lab. He was alone in the evening, and all of a sudden he saw the shadow on this fluorescent screen. He published this within weeks after discovery in Science. This is, I think, absolutely amazing. So within weeks, there was no FDA approvals needed at the time. People immediately used this new technology for image guidance. Yeah, so the first surgery took place in 1896, already using X-ray as an assistant. It also was used in shoe shops to just look at the skeleton of your feet, whether the shoes fit. So people had no idea what radiation does to you, but negative effects it has, but also what positive, like therapeutic effects it could have for radiotherapy. So this was complete disruptive technology which came along, and people were freaked out. I mean, his wife, Anna Röntgen, says, "I've seen my death," when he took the picture of her hand. She thought she saw a ghost, her own death. These days, of course, we've got this whole wealth of imaging modalities, and a lot of effort is done by the major manufacturers, Siemens, Philips, GE, Toshiba, and now United Imaging in China. But we still use all of them. None of them has been replaced or displaced by another. And the reason for that is they are complementary. So they give us some information, but not all. So X-ray mammography is a good example. That's used for screening for breast cancer from a certain age. I think I've got my first one coming up now. But if these things are not clear, if the breast tissue is very dense, for example, the women have to have an ultrasound instead, or sometimes a CT, or sometimes an MRI. So they actually start moving between the modalities quite a lot. Ultrasound is very nice. It's such a crappy image there. I apologize for that, but ultrasound really looks bad. You see lots of speckle patterns, occlusions, and shadows, and if you like nice pictures, it's not nice. That's why I love MR. You see this little fetus there doing little somersaults. It's a fantastic imaging technology, mainly because you can program it. It's actually pulse programming is like computer programming. And you've got this whole wealth there, and you have to deal with lots of different dimensions. Ultrasound can be 2D and 3D, but inherently it's also a time sequence, so there's always a time dimension there as well. X-ray can be 2D, projected 3D, reconstructed, CT 2D, 3D, with time as well, with injection of contrast. MRI can be anything you want, really. It's a completely versatile methodology. And you've got the nuclear medicine ones on the right, which are complementary to the others, so they all have their role. Now, in computer vision, our tasks are quite simple, being a bit provocative here. We want to maybe classify images. You want to say, is there a cat in that image or not? Yes or no. I want a binary answer. If I know there's a cat, I might want to know where is it, because it might be a big picture with lots of other animals, but I want just a cat, so I get my bounding box. So that becomes a localization problem. There might be a whole little zoo of animals on my images, so and that becomes a really hard task. Actually, you have the dog. You have to first recognize it's a dog, that there's a dog in the image, then where it is. You've got a little ducky there. It's not a real duck, I hope, otherwise it won't have much chance of survival. And then you've got two cats there, which you hardly see the second one. And you have to distinguish between the two because they're two separate entities. They both will light up as cats in your feature maps if you learn that, but you have to distinguish them as two separate parts. That's a real difficult semantic problem. It looks easy, it's not. And then you want to segment them, and I think the segmentation here in this paper was just drawn around. It's again not an easy task, but you want to have a logical grouping of these things. So that's, the basic computer vision tasks in a nutshell, and then there are many more complex ones. So in medical imaging, we've got all this. So I've taken these images from the media 20th anniversary issue, where a lot of us have submitted papers to, were invited as guest editors, just to tell what we think, what the past, the future, and the present is. So if you're interested in that, this is where I would direct you to. It's now 2 years old, which, I was laughing when Ken said this is an old thing, it's from 2017. This is how fast-moving things are. 2016. What happened after it is a completely different story now. So this was a good snapshot at a time, but I think we've almost drawn a bit of a red line under that chapter in medical imaging. Just to illustrate the point, we want to segment parts of the body, we want to understand function, we want to model the heart, how it beats, we want to discover whether there's a problem with the strain somewhere. So it's a big playground of problems. I mean, the clinicians have more problems than we can actually ever hope to solve. Yeah, so if you're interested in applying computer vision for a very good cause, that's it. I mean, that's a huge playground, but it is tough. It's really hard. So the tasks in computer vision, I found this, I forgot where, I apologize if I didn't provide a source, but I like that because such a simple graphic might be too small for you in the end, so I might have to read it out. So the triangle on the left is more like a bottom-up triangle, an arrangement. You want to detect object or classify, as I just said, and track them maybe in video frames. You want to then study their trajectory, their dynamics, say pedestrian walking across the road. Yeah, so that's one of the very classic computer vision problems. Detect some patterns, maybe texture analysis. And then you want to do something that you want to maybe think there's an incident, some anomaly happening. For example, you're in a self-driving car and the pedestrian is crossing the road and the car has to react. So you have to make that logical link that you have to brake, or the car has to brake. If the car doesn't, you have to. And then on the other side, you've got this more top-down approach. What you really want to do, you want to understand this scene. So you have to bring in your domain knowledge. Is it indoor? Is it outdoor? Is it foggy? Is it cloudy, rainy, light or dark? And then you've got lots of rules. You've got, for a self-driving car, for example, you have to stop when there's a red light or there's a zebra crossing, there's a pedestrian standing there. So you have to apply those rules. It's kind of boundary conditions for your problem almost. And then you kind of narrow it down to all the things you need to kind of study and apply those rules to. And this is like the logic, the physics of motion, the local intensities of image pixels, statistics, and all this. So this is kind of computer vision rolled up in like two little triangles, which are very much interacting. Now, in medical imaging, we've got one big triangle, but it has probably more problems, and you can probably transport it to the computer vision triangles a bit better, but I wanted to actually tell you where we're coming from. So from the bottom, we have to acquire images. Now, that's a problem on its own. I'm not a medical physicist. I usually take images, and I'm glad if I can convert them from DICOM into some image format which my tools understand. But you have to acquire them, and that's already has to take care of patient positioning, of what contrast is used, and so on. So there's a lot of thought in there already. Then we have to reconstruct them, because they don't come just like a printed Polaroid picture into your hand. You have to actually do something with the data you scanned. So it's actually you have to really do a 3D reconstruction of a lot of data measured. Then you have to do something, usually some enhancement, some blurring, denoising, and then you want to interpret this image, and that's usually segmentation. Yeah? You segment, say, the liver or the heart or the brain, whatever you're interested in. It's usually fairly standard. But then you want to do something with that, and then we go into imaging biomarkers, computational biomarkers, not real biomarkers, but they could be indicative of a disease. So you want to say, has the hippocampus shrunk in the last year? So that could be an indication that you are on track of developing Alzheimer's, or has the tumor grown, or has the tumor become more perfused, and that affects your treatment options. And it also is for detecting of disease in the first place as well. So is that tissue healthy or not? Is there fibrosis or not? And then ultimately we want to do diagnosis and prediction. We want to do something with that. We want to actually help the patient. We want to get them to get well and optimize their outcome. We want to optimize their treatment. We want to put them on the right treatment pathway in the first instance. So all these things are kind of done in a very serial fashion, very bottom up. And I'm going to talk about that a bit later, why I think that's not maybe the best approach. But at the bottom of this is a lot of computing, and I actually realized as a computer scientist, this is actually where I can contribute a lot to, because, as I said, MR imaging is pulse programming. It's actually, you only have actually 3 degrees of freedom in MRI, 3 parameters you can tweak, and then you can bring in motion models and other things. So it's actually quite simple. It's not, but it's something where we can, as computer scientists, contribute a lot. These things are generally like in the perception thing. We want to have good images out of it. We want to don't have blurring. We want to don't have noise or shadows, and we want to actually extract information. And then in the end, we want to do some reasoning. We want to actually do something useful for the data. And one reason why, for example, I went not into satellite computer vision, as it was one of my PhD projects suggested to me, looking at satellite observation of people. I said, actually, I want to do something useful with my knowledge. Obviously, you have to know whatever you invent in one field, in one domain, can be easily transported to another. So you can't wash your hands in innocence ever, I think. So MICA is our main conference. Medical Image Computing, Computer-Assisted Intervention. It's not as big as SIGGRAPH. We've grown it by almost 50% this last year, so I'm very proud of that. But 5 years ago, so this should be 2013 on the bottom, this was when you would do a Wordle of all accepted papers to the MICA conference. Yeah, so the basic counting the frequency of words in titles taking out and the and so on. And the bigger the word appears, the more frequent that word would appear in titles. Yeah, so it was pretty what we expected. It was the most likely paper title would have been image segmentation and registration in brain MRI. So if you put a paper in 2013 like this, the chances that you were accepted were probably quite high. I'm a registration person, and I was very pleased to see at the time that registration was very big. It was really because such a tough problem. And brain MRI, the reason we've got so much brain MRI, brain is a rigid body, unless we look at the developing brain or at the deteriorating brain. But you only have to do rigid registration, then you're good. And MRI is non-ionizing. We get volunteers. We had more data. So actually, it made sense. Now, 5 years on, I was MICA program chair last year in lovely Granada, and this was the Wordle I took out. First of all, we had 50% increase of submission. It was the biggest conference we had, but it's still tiny compared to SIGGRAPH. But this is what happened in 5 years. In 5 years in a community, the most likely paper title was Image Segmentation Using Deep Learning. And you might not even see where registration sits. It's somewhere between using and network. It's gone. It's almost dead. People think it's a solved problem, which it's not. But the whole community is now focusing on segmentation because it's the easier problem to solve with deep learning, because deep learning AI is so hip right now. Everybody wants to do it. To a degree that new grad students starting now have no idea about basic image processing anymore. We have to teach them how to do a convolution, how to segment, how to do edge detection, all these things. They don't do that because they say, well, it's done, it's gone, you know. Yeah, so it's quite interesting for me. So I had to retrain myself in the last 5 years a lot as well. So what happened in the last 5 years? Well, artificial neural networks happened. Computing power, GPUs, was a huge disruptive technology for us, having more of that. Annotated databases, ImageNet 2010, computer vision is always a couple of years ahead to us. But actually, if you look at this, a lot of these things happened much earlier already. Artificial neural network is an old concept. I did that as an undergraduate student. I implemented backpropagation. It was not new. It was always there. But I think the trick was the combination of these three happening at around the same time, which then stimulated the entire community to shift gear and do something new. So AI was the answer. So that's basically the creation of intelligent machines that work and react like humans. It was always very ambitious to do that, and if you look at Google Images and Google that, and you find all these fancy robots, and they look like humans, strangely. I don't know why they have to look like humans. But they have this high-wired brain with lots of neurons. Of course, our brain still has more neurons than any of those computers we're looking at, but you know, this was always the vision. And it's about intelligence demonstrated by machine in contrast to the natural intelligence by humans or animals, or we call it quite often just human animals and ignore human intelligence and ignore other animals. And well, since we're in the birth country of the Terminator, I think this was one of the gear shifts as well at the time. So Arnold as the Terminator, human outside, and then machine inside. And then if you go into Terminator 2, he becomes more and more human. So he adapts. He starts developing emotions and so on. So that was an interesting development. Skynet were the ones, so you might not remember that from that movie. Some of you might be too young to remember Terminator at all. But Skynet were behind that creation of that first arm, which they have to destroy in the Terminator 2. If you look at the small print of Skynet, it says neural net-based artificial intelligence. I can't remember how old Terminator was. It must have been like late 70s, early 80s, I would say. Yeah. So neural networks were there. Artificial intelligence was there already, and they picked that up, which was quite cool, actually. So even though I live in Britain, I'm not British, but I still think that Alan Turing is the father of AI. He was the one who cracked the Enigma code. And he stipulated in 1947 that one should consider the questions, can machines think? So he was the first time thinking about, could we create something which is not human intelligence but artificial intelligence? It was really... he was really a pioneer in that. So he wanted to really test the machine's ability, whether it could exhibit intelligent behavior, which you can't distinguish very well from that of a human. Yeah, and it was tested on natural language conversations. And the test was quite simple. So if we've got one person, C, sitting in front of two screens, they don't see what's behind those screens, and A is a computer, and B is another human. There were also blinded studies where there were two humans or two computers behind the screens. And then C asked some questions to both, and they have to respond, and they just get a printout. Otherwise, it would be cheating if it's a hand-scribbled note. That probably would have revealed it. And if the C could not distinguish or say who is the computer or not, the computer, or basically the machine learning program sitting inside the computer, running on the computer, would have passed the Turing test. Yeah. Now, it depends, of course, which human you put behind the screen. And sometimes it's hard to tell. And especially, I think on Sunday, this was the tweet which really killed me. So, build a wall and crime will fall. I grew up in Cold War West Berlin, and I've got a certain special relationship with walls anyway. I might as well, I really thought I should apologize if I offended anybody. And there might be a Trump supporter in the audience by accident. Probably at the wrong place. But I could have put up Theresa May saying Brexit is Brexit, would have had the same effect on me. Anyway, so the bar could be pretty low for the Turing test if you're not careful. You have to set it up better. So artificial intelligence, machine learning, deep learning, as I said, are not new concepts, and it's a whole timeline which you can look at. So it started probably in the 1940s with developing the first computer. Without that, you could not have done that. Then there was this first AI boom in the 50s and 60s. Alan Turing, of course, always a bit slightly ahead of that. And then have the second AI boom, the AI and there were 2 winters around that. So the first winter was people just did not know what to do with that. I mean, they were able to land on the moon with something which is much less than a smartphone, right, if you think about that. But they couldn't really develop more algorithms at the time, and they didn't have the computer power to really do intelligent machines or develop them. But they did instead, they resorted just to the rules. So expert systems, information systems were everywhere. The first chess computer, I think deep thought and all these, they were just literally just learning the rules, learning then a lot of past games and then trying to go there. But they had a limited success, and at least they got me interested in the topic in the first place. And then we followed this second AI winter, and then in the 2010s, we are all in machine learning and deep learning. All of a sudden, Toronto is one of the epicenters with Google Brain, are quite big. You probably have seen all the news, IBM Watson and Go, the Google DeepMind coup of beating the grandmaster of Go. But actually, if you look at 1979, the basic theory of convolutional neural networks were already developed. Yeah? So, and not much has changed since then. Yeah? So the theory was there since 40 years. Yeah? Okay, so we're here now. And of course, they were inspired by neurons, by synapses, how you train brains, and kind of try to translate that into neurons and layers and all that. You have an input layer, an output layer, and you've got lots of hidden layers, and you train the connections and thicken or increase the weights. And that was the multi-layer perceptron, which is there since the 1960s. Yann LeCun basically took Fukushima's first convolutional neural network to the next level in the 1990s. So he's at NYU, like Ken is, but also at Facebook in Paris. But at that time, he was literally just developing a number recognition system. So the output was between 1 and 10 or 0 and 9, depending how you count. As a computer scientist, you always start with 0. But he wanted to just recognize these MNIST database, these digits, whether this is a 1 or a 2 or an 8 or whatever. And this was like alternating between now convolutional layers, which kind of group neurons together and get like a joint response. We train little filters, in effect, rather than fully connected neurons, because that is numerically explosive. So that made it work on computers in the 1990s to recognize numbers. Yeah? So that's why we were there. And nowadays, it's, with ImageNet and so on, now we can train on cats and dogs, and we can say, is it a dog or a cat, or is it a cat? And the principle is the same. We've got convolutional layers. We kind of have this max pooling, where we just group together, go into, group the responses, go to a lower layer, so do downsampling there. And then in the end, we have to have some fully connected layers, but we are downsampled so much at that time that it's actually numerically feasible. And then marry that with GPUs, you were in business. And there are lots of challenges going, and lots of different network architectures were developed around that. Of course, you want to go one step further. You want to not say, is it a cat or not? You want to segment the cat, so you have to go all the way down to recognize the cat, and then go all the way up to assign to every pixel, is it a cat or not? Yeah? So that's a very basic segmentation task. It's not that easy, of course. You have to do lots of post-processing. So that was nice. And then you've got also a cat and a dog in a picture, so you want to group them also maybe into foreground and background. So the task became more and more complicated as people grew with the technology, which they all of a sudden had. And the way it works is you look just at the cat region, for example, and you get a response, like a filter response, which says, yeah, I think it's probably a tabby cat. And then you accept that at some point, and then you can then map that back, and then you get like a heat map which tells you there's a cat in that area. And that you can use then for your segmentation. So in medical imaging, we want to do a little bit more. We want to we maybe get not really nice cat and dog picture. So our very basic thing, if you remember that pyramid I've shown you in the beginning, it's now lighting up in red at the bottom. We're looking at image acquisition and reconstruction. So we get an image like this, which is heavily undersampled, violating the Nyquist theorem and everything, and we still want to get a good image out of it in the end of the day. But maybe the first step is just to say, this is a bad image, I can't do anything with that. Even if I could segment it, I'm not trusting it. I can't do a medical diagnosis with it. I have to discard it. I have to recall in the patient, do another scan. If I could do that very quickly and the patient's still lying in the scanner, that's good. That would save money, right? So there's a lot of healthcare economics in there. So classifying an image into good or bad is a very basic task which can be done with neural networks, because we're very good in making images look bad. We can take good images and deteriorate them. So we can grow like a database of really bad-looking images and then train neural networks, and then it discovers good from bad. It's a bit like Cinderella, right? You're picking the piece from the crab. So it's basically a similar thing. It's like looking at a cat picture and say, is it a tabby cat? We say not only a tabby cat, but is it a poor quality image? Yeah. So it's the same principles. There's no magic in there. We also want to restore it. So just saying it's a bad image, try again, is sometimes not good enough, because quite often we look at historical data. We have a patient at a certain time point. We look maybe at their lung nodule and want to see, has it been there last time we saw him? Because it might be a patient with pulmonary disease. Could we have predicted it better? Could we go back in time? If we could go back in time, could we predict it? So if we would now scan somebody who looked like this patient but 2 years ago, could we make a better decision support after this? Could we say, this looks bad, we have to do something, at least stop smoking at this point? But there again, it becomes like a task of really recognizing good and bad images from one another, having a database, annotated database of good and bad quality images, and then training the network to make a bad image looking like the good one, like its good version. That's an easy task, because we can deteriorate bad images. So we can hopefully reconstruct then images which look better. We can do that, by the way, for those interested in the spatial domain, and that's a simple computer vision task. So denoising and all these things would do exactly that. It's the same network architecture there. But we can also now start doing that in the spatial frequency domain, in case space, where the MRI is not even reconstructed, because all the information is there. The reconstruction doesn't add any information. If anything, it adds blurring. Yeah? So that's quite interesting. So we can actually apply computer vision principles quite nicely. And of course, one of our issues is there we don't have 2D images, we've got 3D volumes, which is a bit of a bummer sometimes. I think the one area where the medical imaging community maybe contributed a little bit to the computer vision community was exactly in that we needed 3D segmentations. We needed efficient 3D segmentations which could segment multiple objects simultaneously. We not just want to extract the myocardium, but also the blood pool and the right ventricle. So we've got this multitask classification and segmentation problem. And this is when we go into the segmentation layer of our little pyramid, and there were at least one approach, UNet, was first presented at MICCAI, which is surprising in a way. It's the most cited MICCAI paper of all times, and I think it's 2 years old. It completely has bumped me down from my top 10 position. I think I'm not top 10 anymore. But UNet, Olaf Ronneberger is by Google DeepMind, is at Google DeepMind, and this is basically a very efficient way of going through convolutional layers, max pooling, so going down, going back up again, as we did with the fully convolutional neural network, which I have shown before, but also having lots of nice skipping layers, which actually make it just more efficient, and it's in 3D. Yeah, so this was a nice thing. Right. Moving up in our pyramid, of course, we want to do something with our information. We want to segment our images, but then we want to do something. A very easy task in cardiac imaging would be you want to calculate the ejection fraction. So you want to look at the blood volume at systole and at diastole and calculate the fraction, which could indicate to us how well is the heart still pumping. It's a very basic test. You can use any segmentation method you want for that, if it works. And of course, people now use just UNet for that. But then you want to do some clinical diagnosis with that. So you can combine it with other factors you might know. This is not my work, I just added this. If you want to see whether there's pulmonary hypertension, you can just add more data and also train the network on that. So you can actually start bringing more and more information together, moving away from images, but moving to clinical records, other data, other things you know about the patient. It's still a very serial approach, so we step through our pyramid from bottom to top. We sort of acquire and reconstruct images, segment them, and then we analyze them. That's how it always has been, and nobody has been really challenging that for a long time. So I want to spend a little bit words about big data. I mean, this was mentioned in the previous talk. Whatever we do, wherever we go, we're being recorded. We are part of the big data collective crowdsourcing community which supplies data. So what is it? It's extremely large sets of very diverse and multimodal data. Multimodal not in the medical imaging sense, it's CT and MRI, but multimodal is just, it could be completely different formats, right? It could be something could be imaging, it could be annotations, it could be anything. So it's big, that's the main thing about it. And we want to analyze it, so that was usually the technique known as data science. It's kind of this big umbrella arm which also encompasses statistics and cluster analysis, so unsupervised analysis, then also machine learning and deep learning as a subdiscipline of machine learning. And we want to do that to reveal things which we couldn't see before. Basically, it's too much data. If you want to look at a lot, we can't see patterns very well if you're like in a space which exceeds 3 dimensions. Maybe with Ken's tool we can look into 4 dimensions, but at some point we just don't see it. We can't look at clusters in that space anymore. We want to see some trends, we want to see associations, and basically want to understand what's going on, gain new insights. It's also about knowledge discovery and not just about training good or bad, but actually saying it's good but, and gaining some new knowledge. So how big is big? Well, I looked at this 2 years ago, and I should have updated this, but 90% of all the data that today, which exists today, there's data everywhere if you look around you, was generated over the past 2 years. And I dare say if I would have updated that sentence, it's basically all the data that's generated today was produced over the last 6 months maybe, yeah? It's huge. At that time it was 2.5 quintillions of bytes every day. I had to look up what a quintillion was. It has 1,018 zeros. That's a lot of zeros, yeah? It's a lot of data. And that doesn't, I mean, medical imaging is a very tiny fraction of that. It's more the other things, like my watch measuring my heartbeat, for example. We're collecting data continuously. Yeah? So it's almost data pollution, what we are living in now. So you want data, here's your data. So there's nothing that actually stops us now from exploiting that data and using it, unless there are privacy laws, patient ethics, the big discussion, who owns the patient data? That could be a nice this topic for discussion, because that's not clear to anyone. Is it the hospital? Is it the NHS or your local private insurer? Is it the patient themselves because it was them being imaged? Or is it the company which paid for having this patient image? So there's lots of issues there. And what can we do with that data of every patient ever scanned, ever examined? What are we ethically allowed to do? What should we do? And there might be competing arguments, right? If you could solve cancer, I think there is a moral obligation to actually examine all data, but it comes at some cost, maybe. So big data and computer vision is probably not a problem, although I think they still need more data, more annotations. We need to move into the semi-supervised and unsupervised area as well, but it's great to have this as a good starting point. Not sure whether it's enough. I'm not a computer vision person per se, but I looked for video sequences. I found much less in computer vision, annotated video sequences. There's some database on stereo views, but you want to play around with data. You really want to benchmark yourself as a scientist, how are you doing compared to the rest of the community, and for that it's quite good to work on the same data, and that's why ImageNet was a good starting point, like a challenge. In medical imaging, what we see now emerging is population databases, and that's not necessarily patients. In the UK, we've got UK Biobank, to which everybody has access. You can apply and get all the data you want. There's a bit of a problem because it's a population study, which means these are not all patients. They might actually have something without knowing, enrolling it. There will be a positive bias in that patients volunteers are more likely to be healthy than not, because otherwise they wouldn't volunteer. If you're a bit worried about your liver or something, then you might not volunteer for this, right? So there's a bias in there. But lots of patients might also sign up because they say, well, the more imaging they get, the better it is, right? If they could help other people, that's good too. And what we run in the MICA community is something which is quite cool. These are grand challenges in biomedical image analysis. It's a bit like Kaggle, and sometimes there are medical imaging challenges in Kaggle. There was one on predicting outcome from baseline lung CT images. You had to say, will the patient still be alive in 5 years' time or something? And you could win $1 million, so that was quite nice. I think if you win a challenge at MICA, you maybe win an espresso machine or something on that level. But you get they're quite nice challenges, segmentation challenges. There's always one called Starcom where you can win probably an espresso machine or maybe some capsules at least to segment the heart accurately. And you're comparing yourself against a clinical expert who had to sit somewhere in the basement of a hospital and draw around the myocardium all day. And then that helps the community to grow and to benchmark. Competition is good because it helps you to become better yourself. So these are quite helpful, but they're not necessarily asking clinical questions. Yeah, they just say, how good is your segmentation? How good is your registration? How well can you track this ultrasound image? They're not really tell you what to do with the data. The biobank is the opposite. You just get the data and they say, here, go away, do something. There are no labels in there. The nice thing about biobank, though, if you do something with it, if you generate labels of some sort, so we get your local radiologist or their trainee to draw circles around myocardia, and you train a network to do something and segment the rest of the database, you have to submit your results back into the biobank. So it's still a collective effort of the community. So it's a bit like crowdsourcing. You crowdsource patients or volunteers to be imaged, and you crowdsource people to do something with that. And everybody should benefit from it in the end. That's the overarching principle there. But yeah, when you start, it's quite hard to get started because there's not much in there yet. So because of this lack of data, these population studies could be quite interesting. And what we'll get from UK Biobank in the end is imaging data from 100,000 subjects, including follow-up data. So we can go back in time with these people. We can look at them, how did they look like 5 years ago. And I hope they will keep this running and will recruit more people. You get all bits. There's a whole body MRI. You can look at the brain. There's function MRI of the brain. You can look at, it's not just this image you get of the heart. You get very specific, highly quality controlled images of the heart, cine images, perfusion images, and so on. You get CT, you get PET, you get X-ray, but you get more than that. You get information about the people, their lifestyle, whether they smoke or not, their clinical records, whether they've got diabetes or not, and their genetics with samples. So it's a brilliant data main. It's only 100,000 people, though, so for me it doesn't sound like big data just yet. I know there are other studies. I think there's the Rotterdam study. We kind of image a whole suburb of Rotterdam and follow them up over years. So I think eventually one has to group this. Also, this is drawn across the UK, which have their own eating habits and their own lifestyle and maybe higher obesity than parts of the rest of Europe. So you're looking at you can look at the ethnicity, by the way, which is quite diverse in the UK. But yeah, it doesn't apply to like a small town or huge town in China, right? It's not, you can't translate this so easy. So it's a different domain. So you have to be aware of that. So I wanted to talk about 3 applications. Maybe this is the ones I'm working on, but I thought I'm just using them for illustrative purposes, not to promote my research in any way. But I think these are quite relevant ones. One is on cancer, and I'm sorry to say 1/3 of us here in the audience will develop cancer at one point in their life. And what we do in medical imaging, we hope to improve outcome, that you survive the cancer and don't die of it. And probably each of you knows somebody who has cancer or had cancer or who was lost to cancer. The other one is cardiovascular disease. Again, this is the biggest killer, in fact, because it's linked to so many other things, to diabetes, to obesity, to lifestyle, smoking, alcohol. All these things play into that. Bit into cancer as well, lung cancer or liver cancer. And then like a little hobby of mine, but I think it's just such a nice thing, is fetal imaging. People like kids normally, they like babies. But if you can intervene at a very early stage in life, pre-life, almost, is fetal, you could also improve outcome. Yeah, you can improve the neurocognitive abilities of a child by detecting abnormalities early, maybe delivering early, or looking whether maybe the placenta is not working anymore. So you can do something about things if you detect things earlier. So fetal imaging is where things start. It's really, if you're on the wrong path at the start of your life, you are more likely to develop all other kinds of problems later. So it's actually very important to not forget that. It's very hard to get funding in fetal imaging, by the way, because people focus on cancer, on cardiac. That's why I'm throwing in fetal every now and then. So big data in cancer imaging is not big. It's not as big as we wish, at least. Normally, we only have a small number of patients from dedicated cancer drug trials or radio tracer trials or whatever. And with small, I mean, we get ethics approval for 10, 8 show up, and 3 drop out. Yeah? So we've been looking at 5 patients in the end, and my student has to do a PhD around that, even though everything was set up. It's really hard. You can go into multi-center trials, multi-center studies, but there you have to deal with very heterogeneous data, different scanners, different scanner protocols, different treatment plans for the patients. If you want to monitor, maybe in cancer, whether a person is responding over time or not, you don't really know what's going to happen to them. You don't have a direct comparison. But on the upside, every single image is very rich in data. It's very dense in information. It's not just a cat and background, right? It's the cat has whiskers and has pupils, and you just kind of have to think of it that way. So we've got 13 million image voxels in a normal volume. And it could be any kind of volume with contrast. It could be, it could even have a time dynamic curve. And we also have all these non-imaging data points. So just to illustrate how much data this could be, this is biphoton microscopy, where you get 2 volumes. One here, in this case, fluorescently labeled for the endothelial cells, and one for the tumor cells. It's in registration. You image both at the same time. And the little red squares I'm drawing in there just shows you a single tile in this volume. Each tile is 512 by 512 pixels. We've got 30 slices, which we probably use, but there are 60 slices, and we've got 12 by 12 tiles per whole scan slice. So that gives you 2 billion pixels for a single tumor. Right? So that's serious data. The data looks quite similar. So you've got you see just the vasculature, the microvasculature of the tumor, which is really important to understand if you want to know where is the tumor growing, is it starving, is it reperfusing, and that could inform your treatment plan. But you want to get out something like this in the end. It's a bit dark, but you want to get out this chaotic angiogenesis, this neovasculature of the tumor. And the challenge there is to get annotations. I mean, I could not think of any radiobiologist who would want to sit down and label how many billion pixels, right? So we had to come up with something very simple, and it's kind of like a little doodle. And I've seen this as CVPR in 2016. I thought, this is cool. This is when I start learning. I don't learn at MICI, I shouldn't say that, but I learn at CVPR. This is where I get the newest ideas. But people were looking at just, okay, if you could do little swervy lines in the image, this is background, this is vessel, this is the lumen of the vessel, and just do it on a couple of tiles, because they look all quite similar, all different in morphology and structure, but the texture and so on is quite similar. And we help them a little bit by throwing in something called superpixels. We get actually a couple of annotations for a single tumor, and that's enough to actually train a network to segment the rest of the tumor. And you do it a bit in interaction, you keep the human in the loop. So it's called active learning. And then with that, you can segment your billions of pixels. And of course, you've got all these networks which do that. The problem there was 3D is too big for this. 3D convolutional neural networks would not have worked on this. It's just we still don't have the computing power. We're still looking at Moore's law and say, okay, we have to wait another couple of years. So we did a time labeling of the data by saying, okay, adjacent slice is a bit like a time component. So the third dimension is time, and then you sort of feed back a bit of the information. It's a bit like cheating by doing 3D filtering of a volume and then segmenting it slice by slice. That's the equivalent, actually. And it works better. It's not perfect, but it works better, so we did that. And with that, you can have tumors grow over time, so you can watch them grow, which is stunning. I'm sure you've seen images like that, having an isolated tumor, watch it 10 days of growth, basically. It's just 8 scans, but 10 days from day 1 to the last day. And that you can start learning something. You can extract things like the tortuosity, the branching points, and so on. So this could be really useful in thinking about how could radiotherapy be improved. But of course, it's quite different to just segmenting a cat. So we learn from computer vision, but it doesn't take us all the way. We sort of have to become a bit more creative, deal with our larger data, and the problem is always the training data. Right. So this is the more visionary part of my talk. Just let me know how I'm doing for time. But we start at the bottom of our pyramid normally. We acquire images. We are in case space, for example. If it's MRI, it's like a Fourier space, spatial frequency domain. We reconstruct the images. That's why we needed computers for medical imaging. CT would not have been possible without computers. They were probably the first ones to use them. So we've got nice images, then we do some nice image processing, analyze it. So maybe it could be deep learning at this point already. We define the relevant information. We're stepping up and up in our little pyramid. And then in the end, we've got maybe a nice model of the heart, and we can analyze it and do maybe computational modeling and other things. Right? But it is a very serial process. We don't make use of the fact that we've got the entire pyramid at our hands. We just go through it one by one. Yeah, so we neglect information almost from the previous level. We always take the output of the previous level as input to the next level, rather than integrating that a little bit more. So this is when we actually got together. This is a large consortium in London with Imperial and Oxford. Oxford are the odd one out there, not in London, but Queen Mary and King's. And we said, we actually want to do it end-to-end. End-to-end is this thing in deep learning where you say you throw something in and you get something out and you don't really care what's going on in the middle. You optimize everything simultaneously. Say if I wanted the ejection fraction of the heart, I would acquire the images, wouldn't bother about reconstruction, and get out the ejection fraction somehow magically at the end. It probably goes through all the steps in between, has to estimate the blood volume at some point to calculate the ejection fraction, or to estimate it at least, is a different story. But this was the idea, that we say, actually, we don't want to work separately anymore from the MR physicists, and we don't want to work separately anymore from the clinicians. We are the piggies in the middle as imaging scientists. We want to bring it all together. We should work together. So basically, we want to do that step from the bottom to the top of the pyramid a bit more efficiently. So cardiac imaging, I mentioned quality, poor quality, good quality, and compared to saying whether it's a tabby cat in the image or not. It's a simple binary classification task. Yeah, so that was our first goal. So we had good quality images. We've got poor quality images. Problem with UK Biobank is it's nicely curated data. So a lot of images, there are not a lot of images which are of poor quality. It's also volunteers. It's healthy volunteers a lot and not patients, right? So we actually had only a few subjects which actually had poor quality data. So we say, that's great. We can make data look bad. That's easy, right? It's called data augmentation. So we do this. And the new thing there was probably to say, we don't just add noise to images. We actually go back in case space where the images were produced in the first place and emulate what would happen if the patient would move. Because what happens then, you mix up by accident lines of case space. Yeah? So it could be complex things like breathing motion here, even but just looking at something much more simple, that's cardiac triggering. You just sample, you fill the wrong volume with the acquired line of case space. So if we understand that, we could go from good quality images to bad quality images without a problem. That's easy. The trick is to go backwards in the end. But we can really do corrupt images quite easily. We can actually take a good quality image and look at like an image where there was mistriggering of the ECG signal. And there's a real motion artifact image. It looks a bit like it's blurred through the myocardium. You see like several cardiac phases at the same time. This is what's happening at mistriggering, right? And it's not good for diagnosis. Well, you think data augmentation is a bit like that. You wiggle around, you input a bit, you move it around, you perturb it, and this is exactly what we're doing. We're just adding some bad samples to get a balanced training data set. And we do that by looking at our individual frames, and then identifying case baselines, which we then swap between frames. And then we just reconstruct normally doing inverse Fourier transform. And then any network would do almost good quality or bad quality. Is it a tabby cat or not? Is basically a simple classification problem. That allows us to identify the unseen data, cases which are not good. Okay. Now, the next thing was to go one thing further and say, okay, right, I know it's a bad quality image. Can I do something about it? Do I have to throw it away? Do I have to recall in the patient? Or do I have to give up on that data because it's 5 years old and the patient is not there anymore or has died? Or I still want to use that data if possible. Yeah? And the question, I'm not going to talk about the details there, but it was, again, can we go from case space before the image was even reconstructed, because this is where the damage was done already, can we correct the artifact automatically? Yeah? And we do a little bit of a trick, which is putting in a discriminator in there. It's like a generative model. So that's what we do. We sort of go into case space. We use one of our own motion-corrupted images just as a test, but of course we apply to unseen data as well. And then we get something out, which I think, and that's sometimes the advantage if you're old enough, like me, it looks like anisotropic diffusion. It looks just like nonlinear filtering. So I think these are the things, as a devil's advocate reviewer, I would hope I would get that question, that my postdoc actually has to do a comparison there. But it was done in a neat way, and the idea was, of course, doing the corruption in the right way and not just adding noise or something. So this then helps us. There's an original image, a corrupted image, and a corrected image using our method. Now we want to go into segmentation. Say, has that helped us, right? So looking just at any odd UNet kind of segmentation method, our original image is the ground truth segmentation of that, but we also applied UNet to it to see whether we could recover that. The corrupted image, it fails. Segmentation fails. You really can't do anything with that. With our corrected image, by using our little trick for the correction, we actually can recover a good bit of the segmentation. Now, if you're eagle-eyed and nagging like I am, I would immediately say, because I'm a registration person, this is not the same image. It's not pixel by pixel the right quality, but maybe it doesn't matter. Maybe if you're just after ejection fraction, it doesn't have to be an accurate segmentation. It depends on your clinical question, right? So my last bit was on fetal imaging. Ultrasound is nice. It's non-ionizing. You can bring it to the bedside. It's cheap. It's the only drawback is it's terrible to look at. You don't see. If you see the first sample ultrasound, you don't see. Your first baby, maybe you don't see it. It's like this little peanut which somebody convinces you this is a baby and you have to believe it because it's just noise. But what we did there is saying, okay, we want to have a workstation next to it and actually have a bit more intelligent machine. So basically thinking about the ultrasound of the future. Ideally, we would have it in the ultrasound, only the FDA approval, CME marking, scanner manufacturers don't allow us. But they allow us to stream out the data. So we get the data as it is being acquired. We process it as is being acquired, and we display it on a separate screen at the moment. Yeah, we could have a little laptop. The laptop in front actually is already quite helpful. So that's quite nice. Because ultrasound is a very observer or operator-dependent modality. Depends how you wiggle the probe, how much pressure you put on, whether you're very experienced. You have to push the baby sometimes that it's cooperating and turning a bit, otherwise you can't see the head. So you get very varying quality. There's absolutely no reproducibility in ultrasound. It's terrible in that respect. MR scanner, you pop them in and they move a bit or something, but ultrasound depends actually how you acquire the images in the first place. So the damage is done at the time of scanning, definitely. So our idea was to say make it simpler. So we just let people scan, and we detect things for them, and they can fill out their report maybe a bit quicker. So one thing was to say, well, can we just identify organs of the fetus? Can we say this is heart, this is lung, or chest, or thorax? This is the placenta, which is important to look at as well. It's not done in ultrasound normally. There's the spine, the abdomen. So in your 20-week scan, which is the big organ scan, can you find these organs quicker? And can you then focus into them? So what we did is exactly that. We did is a simple object detection problem, like finding your tabby cat and your dog in an image, but doing it over time. Yeah, so as you scan, it's literally the scanner is on. As you scan, you look at the screen, and you see basically a bounding box that somewhere inside there is something, placenta. It's not a proper bounding box. If you look at the head, that's the easiest to see, the bottom on the left. It doesn't go round the head. It's just threshold at the attention map, which the network spits out for you. It's a neural network approach, of course, but it helps us to actually label the data as we scan it, which is really quite helpful. So it's the same problem, basically, from computer vision straight into ultrasound. And This is just telling you the numbers. Again, subjects numbers are low. We looked at 20 subjects. Mainly, it's difficult to get more. Well, we have more, but getting through the data takes some processing time. But each subject has a couple of thousand frames, yeah, because you just keep scanning through, right? So we keep all the time components. Normally in ultrasound, they only store the screen snapshot, the pleasure picture for the parents to take home, and those few screenshots where they actually measure the head circumference and other things, the diagnostic ones. But we keep everything on data, and we will continue to do that. So when we do that, basically, we only do soft labeling. We don't say this is this is the circumference of the head or something. We just say there is a head somewhere in this scan. So we can do that very quickly. So we, again, set up some GUI which helps clinicians to do that quicker, and then actually can compare to where they actually thought. We actually ask them to draw around, but of course it's not a segmentation or localization problem, it's more a detection problem at this point. It's not fast enough just yet. We haven't quite optimized. So ultrasound frame rate is 40 frames per second. Runtime performance is 15 frames per second. But like every third slice, you probably, as you image it, would get labeled this way. So that's probably good enough. And then finally, this is not computer vision, but it's also, again, thinking a bit outside of the box. When we scan a fetus, if they're getting bigger, 20 weeks, you don't see the entire fetus anymore. You only see parts of it. That's why you have to move around and detect organs. What we got is a multiplexer. So basically, we can have up to 4 ultrasound probes at the same time scanning the patient. They'll have to alternate. They don't scan actually at the same time. They have to, each frame is then taken from a different probe, but you can have them at different positions, which gives you a larger field of view, very simply, which is quite nice. So you don't need to do an image processing solution where you kind of compound scans with image registration. You can just get the data directly, which sometimes the simple things work best. It's just a 3D printed holder for, say, 2 ultrasound probes. We've got now one with 3, we've got one with 4 arranged in a square. And the 2-1 is really nice, quite lightweight. So the radiographers like it. They just scan 2 instead of 1. The angulation has to be quite nicely calibrated. We do tracking as well to help us. But actually what we get then is a view from one probe, a view from another probe, alternating frames. So there's a bit of motion in between, and then we can fuse them just directly. We do some clever fusion now as well to look at image structure, but we can see the whole head. And that reduces shadows and artifacts because we can actually suppress things from one frame and enhance them in the other. So that's quite nice to increase that. And here's just some visual to show you that, so we can actually see. You almost don't see where the 2 cones meet in the fused ultrasound. Yeah. Right, I think I'm almost reaching the end now. So this is just another demonstration. It's built into a workstation. It can be used. We can also directly put the organ labeling into this. Right now we have it only for 1 probe, but we can do it for 2. So we can bring everything together. We can actually provide the radiographer now with something which really helps them. It doesn't help them to scan faster, unfortunately, because the probe is heavier and they have to find ways a bit. But these are the things you have to test. And I'll work very closely with the radiographers there. And then finally, this is really cool. This is if you just scan and you are a novice like me and can't scan, this is what happens. I mean, the fetus is moving around and you're following a moving target the whole time. Yeah, it's 3D ultrasound, just shown in 3 views. But we can actually register them. I'm not going to detail that, it's in that paper, but using, again, a deep learning approach. And so we reorient the data as we scan it automatically into the same plane. So we get basically the view as if we would have an axial, coronal, and sagittal view. Even my probe is somewhere completely different. And that's quite curious. So the radiographers loved it. They said it's a completely new way at looking at a fetus. We can also use it to average a little bit between those scans because that helps us to pop up the signal, increase the signal-to-noise ratio, remove shadows. So these are the things which are now thinking this could be really interesting. Combining that with multiple probes, I mean, I think the world is your oyster in this area. So coming to my end almost. Lots of challenges. Computer vision community, I'm so envious, is so much bigger all my best grad students go immediately to industry. I mean, one postdoc, I've shown the work on the tumor musculature at DeepMind now. They just suck them out. So it's really hard to grow our next talent because they immediately get sidetracked. I don't send them to CVPR anymore because it's just a big, giant graduate fair, right? They don't come back, basically. They just hold interviews there. I mean, they're having suites. I was in Las Vegas at the one at Caesar's Palace. They had suites where they were just interviewing candidates the whole time. It's a bit of a problem. The companies, the big evil ones, are investing now in healthcare, but not necessarily on the right problems. They look at the low-hanging fruit and not necessarily solving them correctly either. So diagnosing, there was one famous paper from Google, diagnosing pneumonia from X-ray makes not even sense. You wouldn't do that. You find it by accident, incidentally, but you would not order a chest scan to see whether the patient has pneumonia, ever. You would hear it, actually. That's what you would do. You would look at other symptoms, high fever and resistance to antibiotica and other things. But it's not even the right problem. So they need our help still. We need their help to actually not suck out all the talent from us. We have the problem of all this variability of medical image data and clinical expert annotation. You think you get a segmentation from an expert, but it's not accurate, right? It's at the end of the day, they just draw things. If you ask another expert, you would get a different answer. Cat or dog is a much easier problem than saying, do you include the papillary muscles or not in your segmentation, and how consistently are you doing this? Plus, we've got our own hospital data to worry about, and that doesn't match well with what's going on in large population databases. We're overwhelmed by what's going on, and it's always the newest deep learning paper of the day. You can't keep up with what's happening. You try to catch the big ones, but even if you then finally said, okay, I use whatever long short-term memory or residual network or whatever, which one should I actually use? How deep should it be? How do I use the parameters? There's lots of fine-tuning. So if you do image processing, you also have to do lots of fine-tuning. It's still the same problem. We haven't got something which designs us the optimal networks yet. So, but we can use several ones of those as an ensemble. So it's classic machine learning. Ensemble of weak learners gives you a strong learner, so that's nice. So you can do that. You still need to adapt them clinically, but the end-to-end solutions become more and more attractive for us. And of course, we've got this curse of dimensionality in medical imaging, but it's also maybe not such a curse. It gives us complementary information and temporal information, which you normally wouldn't have. It's very dense and rich data, so we can milk individual data sets more than we could milk a cat image. So data may not need to be really that big in the end. One thing which is the domain shift I've been referring to a few times is, in the lab, you like nice UK biobank data, it looks nice pumpkins. But actually, if you go out to the real world, you've got something like this. You've got patients who can't hold their breath, and they actually have to do breath holds for scanning, right? It's a involved problem. So you have to be able to transport that and adapt. So in the future, this was a statement which caused a lot of uproar with my colleagues in radiology. Jeff Hinton, the godfather of deep learning, said they should stop training radiologists now. It was taken out of context. He didn't really mean that, but he got a lot of stick for it, and he kind of had to clarify it a few days. But I think he had a bit of a point, because people were scared of this. They said, well, there's this little, I can't see it on my screen, it's too small, I can't see it there, but it's basically a robot ultrasound saying that they had a misdiagnosis, and what should he do now? And he's being sued, or she, I don't know, or it. And the radiographer says, well, sorry, mate, that comes with a job, so nothing has changed. Errors will still be made. So it's important to keep the human in the loop. They have the last call on a patient diagnosis. And there was another quote which said, to the question, will AI replace radiologists? I say the answer is no. But radiologists who do AI will replace radiologists who don't. And that's important. And I've never seen so many new cardiologists and radiologists sitting in my machine learning lectures and doing Python programming. It's part of their training almost. They self-train. It's not part of their medical training yet. I think there was just something in the news about that. People said it should be in the radiology training. But at least they have to understand what this is about, and they shouldn't be scared. They should embrace it as something which aids them, which saves them time. They are still in charge. They are still in the driver's seat. They can hit the brake in their self-driving car. So the human has to be kept in a loop at all times. The problem is human doesn't have a high bandwidth. They've got too much on their plates. So this is where the computer, with the aid of data, can really help them and feed it back to the human. So the human in loop will always be there. It depends also always on the quality of the human. One doctor might not be as good as another one, so be aware. It's not just because there's a doctor in the driving seat is that they can drive, actually. So you have to be a bit careful with that as well. So in summary, I think we really have been really doing well in the medical imaging community to grab great new ideas from computer vision and translate them into our domain. But it required quite often a complex domain shift, and complex in a double sense, because if you work in the Fourier domain, we are already a complex domain. But keeping the human in the loop is difficult sometimes because we need to work across different sites. We've got different imaging devices, and the diseases are very varied. It's just cancer is many diseases, not just one. And of course, we've got the problem that the annotations are not a gold standard. They're errors, actually. We found errors in UK Biobank already, just in saying this is a good quality image. We looked at it and said, no, it's not, right? We had to relabel the quality grades of the experts. And we want to really, in the end, think about why we want to do this. Do we want a segmentation or do we want a nice reconstruction? In the end, we want to improve clinical outcome. So that should be always our end goal in medical imaging. So we have this big vision in our minds. We want to solve cancer. We want to have people die at old age with reasonably good health only. And maybe we don't even need images anymore. That's really, it's a bit scary. Maybe we don't even need to reconstruct. Maybe we can read everything off the sensor, whatever it is, MR scanner or CT or sinograms, and actually get the diagnosis out. We can maybe do these end-to-end things. But I think clinicians and patients would like to see images. They want to look at it and understand what's going on. But these end-to-end solutions could be quite good to have a quick check and give us a faster diagnosis. So we can do that. And there is this class imbalance between computer vision and medical imaging scientists. It's computer graphics as well. I had a dream once to work for Pixar. In the end, it's great to do new movies and have great environments, but you have to think about, what are the important problems in society. For me, it was medical imaging, and I think we could use some help there. Thank you very much. It's 31st of January, so I can still wish you a Happy New Year.
Thank you very much for this very lively and interesting talk. Unfortunately, used up almost all of the discussion time. But
I had 50 slides. How did I do that?
Maybe there is still some question over there.
There's still the panel, I hope.
Hello, thanks for the nice talk. I agree that in the future we will need population databases. But you mentioned in one short statement that there is actually a big problem that if you get images from different score centers, you cannot compare them really. Do you think that AI can help to solve this problem?
Yeah. So I think that's what we need to do. Rather than thinking about standardizing images, which we'll never achieve, I think they're still talking about this, and they should just stop talking about standardization. They should really say, well, you train on one data set, you just retrain a little bit on your own data set, and that's called transfer learning. I think that's needed. So you can even do that going between quite different imaging modalities. And people are doing that. A good example is PET-MR, where you don't have the CT for attenuation correction anymore, but you need to emulate a CT from the MR in order to correct for that and get good PET images out of it. So that's direct application of transfer learning already within one hospital.
Yeah, exactly.
I have a question about the social aspect of radiologists who are reading images. Is it ever the case that their reading is influenced by information beyond the image? Perhaps, what they heard over lunch or what someone mentioned to them in the hallway. Oh, we have this particular patient, and they stumble with their left foot, or some other information beyond the image that actually informs their read that an electronic system would not have access to. Does that happen, and is that an issue?
Absolutely, that happens. I mean, we just look at images. We just look at one little single piece of the puzzle, and the imaging might not even reveal the actual problem the patient has. They might have temperature, they might have, well, the heart rate you might see, but they might have, a little, be a bit wobbly on their feet. And there's a patient record. They know this patient has diabetes already, so they will look at the heart with a different way already. Or they know the patient is a chain smoker, so they're actually actively looking for more nodules. So definitely, this is just one piece. This is why it's so important to bring in imaging and non-imaging data, clinical records together, which is a now newly emerging, well, not newly emerging field, but it's really looking really at big data in the most diverse way. Yeah.
Thank you.
So I have one question about like the deep learning aspect, because you went so much into it and you showed really nicely the like AI and the AI winters. Do you actually think there will be a third AI winter, at least in medical imaging?
Oh yes, yeah. I wish I knew what happens in 5 years' time. And I think it makes really boring conferences now. You just, there's another deep learning thing. If you're not really into deep learning methodology, it's just, okay, it's another application. People get a bit tired of it, I think. But I think it will plateau. One reason why it will plateau is people are not sharing data. So we have to still live with the data we have. GDPR doesn't help right now. It just shuts our hospital down, not sharing with anyone. And I think one needs to become more visionary, and it's up to you in a way to think about what's the next thing. Deep learning only gets you that far. It's currently our Swiss Army knife to do everything. Yeah, we've forgotten almost what was there before. Sometimes I'm quite glad I'm quite old, but I had to retrain myself. I had to go and learn deep learning as well. It will be quite exciting to see what's next. Because integrating everything, say from acquisition to diagnosis, takes more data integration. But I think we have to go probably also back in time a little bit, because we're losing the knowledge of the radiologist, the prior which we put in normally, right? So all the Bayesian statistics, all these things. I think things will start to shift a little bit. It won't be like a new, complete disruptive methodology coming that soon, but it will start harmonizing or unifying what was 5 years before or 10 years before to what's happening now. I think it will augment itself a little bit more, and then it will shift in a new direction slowly.
Along the same lines, I'm here.
No.
No, here.
Okay, sorry.
In case you did follow, I trust you did follow the Watson applications in the medical field in Germany. Depending on how you count, 5 to 7 sort of larger projects, all silently buried. Can you comment on, or did you have any insights sort of why they all failed, or would you be willing to comment on that?
I think they went to market a bit too early. I think, and hadn't it fully tested. I don't have insights into that, but I wasn't surprised, because Watson, they had been announcing that for quite some years, but I didn't really see anything, any new things coming out of that. I was surprised that they went to market, and I'm not surprised it didn't work. I think it takes more time. You need more testing. You need acceptance from radiologists as well. And they need to work within the development. You can't do that just offline. Give me your data. Like Google DeepMind did that to one hospital in London. They went away with the data and it didn't even get permission properly. It will take, but computer-aided diagnosis has been there for a very long time. Actually, mammograms have been read out by computers for 2 decades almost, especially since the advent of digital mammography. So it's just, I think they were a bit too ambitious at that moment in time.
Thanks for the talk. So you showed nice words in the beginning of your talk, and on the second picture, and probably on the first one, I was missing one word, and that was actually validation of your results. Because, 2 years ago, almost 2 years ago, there was the fMRI crisis when the proper algorithms, let me call that, showed 70% of the false positives. And there is also, from the psychology, there is coming this notion of reproducibility testing of the results. And I feel like the AI and deep learning things, there is a lot of reported results, but even in very, very basic research, they find that more than 80% of the positive results reported actually fail to reproduce.
That's quite interesting. But what we did recently, which I wasn't aware of, that shows how new I'm to that field as well. If you train a network several times on the same data, you get a different result. It's because you randomly initialize your weights. You can't initialize them to 0 because then nothing would get trained. And the differences can be quite big. Right, so I think that's something which has been a bit neglected. I like things reproducible. I want my program to always give me the same output if I give it the same input. Right, that's why I program it. Otherwise, I could, do it quite randomly. We do have to validate. We do validate against the ground truth. The problem is already with the ground truth. It's not a ground truth. We're looking more and more into uncertainty as well. Uncertainty of the measurements and trying to put them into the training. So it becomes a bit more robust to that. Reinitializing your model for a few times is probably a good idea. And you're looking at an ensemble of networks, so that gives you a bit more robust output. But yeah, I think it's right. The first, I think, MICA 2017, I was really upset. People just, sorry, looking at your time, are looking just at mean results. They didn't even report on standard deviation of results. I thought, what has happened, right? They just wanted to show pretty pictures. Now you have to test. You have to have several different objective criteria. Some people report on their loss function even these days. I thought, but this is what you optimized, so I bet it should have gone down, in the cost. So yeah, one has to be very careful with that. I agree. Yeah. Thank you.
So we have time for one last question.
Okay, so as I was listening and having been part of working on computer vision in the second phase of AI. Yeah. I have a visceral reaction against deep learning. Actually, in my understanding of it, it's actually quite shallow. And it's a brute force. If you look at the history of AI and what people have been trying to do in terms of computer vision, from understanding how the brain does it from first principles, rather than just throwing lots of data at it. So I'm wondering whether we should take that word deep out of it. Because it really it implies something very powerful, which actually is very dumb. But never mind.
I mean, the word deep is, I'm not, I was very long a skeptic of deep learning. I'm kind of going acceptance. I'm not necessarily a promoter of it yet. I just think simple things it can do really well. The deep is like having more layers than previously. It's a cool name, that's why it caught on, I guess. Yeah, but I agree. I mean, there have been really nice other networks which didn't lift off that much, because mainly convolutional neural networks in some way or the other, but they were like the deep belief networks, which actually were really cool, which didn't lift off for some reason. I think neuroscience, I had a neuroscientist in my lecture the other day, and he looked at all the networks. I showed all the network architectures on one mega slide, and he said, this is the only one. He showed a Hinton's deep belief network, which I think was from 2010, no, 13 maybe, and he said, this is actually how the brain works. So I think we need to use neuroscientists a bit more who can tell us about it. But since we just heard with fMRI, we still don't know how the brain works. I'm not sure whether it can do it. But yeah, it's sometimes it can be quite dumb. I agree. Yeah.
Okay, I think we will have to leave the rest of the questions for the break. You will certainly be happy to answer questions of people approaching you. So thank you again for this nice talk. And now VRVis is pleased to invite you all for a light lunch, which is served outside. Again, we have the 2 rooms. Please spread out into both rooms. We will restart at 1:15. I ask you to be in time. And if you are interested in the work of VRVis, look for the people who have VRVis on their name tags, and you can contact them. They are happy to answer your questions, and we always also look for new cooperations where if you are interested. So see you at 1:15.